I will present the work we have been doing in recent years on excited states in quantum Monte Carlo. I must say that there will be no machine learning, but a fair amount of QNC, and at least I think you can appreciate, you will be able to appreciate how far we can push the type of wave function we use typically in real space quantum Monte Carlo. Okay, so I cannot move. How do I? Okay, good, sorry. So, so we started quite some years ago trying to do excited state calculation for a relatively large system, and then we decided to actually go back to smaller molecular system to really establish whether we are a competitive method for system of problems. Okay, so for excited state, I will talk about variational diffusion Monte Carlo, and the excited state energies, excitation will be computed as energy differences. Okay, and already, if you look in the literature and also for us, we often focus on absorption, which for us means vertical excitation, and already says it can be quite complicated. Okay, so thiophene is a small molecule here. You're having an excitation. This is a vertical excitation, and what I'm plotting is in EV, the excitation is a function of different techniques. Okay, on this side you're having multi-reference PT2, you're having CAS-SCF, CAS-PT2, different flavor of NEF-PT2. These are QNC, variational diffusion for two types of wave function, and this is some approximate couple cluster model including up to 3. Okay, so, and the whole variation is 0.5 eV, and that's large. Okay, so for the mathematicians present, I mean, that's half of the visible spectrum. If you show something like that to an experimentalist, it would be pretty shocked, especially because all of these methods, well, maybe except CAS-SCF, would claim to be close to chemical accuracy. Okay, so the situation is actually not unusual. Okay, we found it in many other systems, as I will show. Indeed, because of the spread, also in correlated techniques, there's been a lot of studies in recent years to establish reference value, establish which technique is best, okay, for these studies. And so there's a lot of benchmarking, mostly absorption of fluorescent. A lot of it came out of the Lowe's, Jacquemin, Anthony Semama labs, but also Cyrus did some work and other people. And I would say for excitation, which are of predominantly single excitation, it has been established that something like CC3, so a couple cluster up to triple approximate, can lead to mean absolute errors which are less than 0.03 eV. So if you're coming in with quantum Monte Carlo, you're trying to convince others that you can do it, we should achieve errors on the excitation of this order of magnitude, okay, which is quite small. Now, why doing excited states? And well, first of all, why are they demanding? So they often have strong electronic excitation, they're open shell. You have quite a wealth of phenomena, you have absorption, fluorescent, intersystem crossing, you have crossing between different states, and the method should be able to actually describe multiple states with similar, in a balanced manner, similar accuracy. And what we are really aiming at was structural relaxation, because if you look at DFT and you move away from, let's say, minimum, you will find that time-dependent DFT often fails. And overall, there are not that many methods which are suitable to actually do so. Okay, so that's what we are aiming at. So now, as regards quantum Monte Carlo, I'm talking about real space quantum Monte Carlo. We are in a good position, after many years, to actually look at excited state and also excited state relaxation, because we can compute efficient derivative of the energy for parameters and determinants. Okay, so here I'm showing some old work of ours. We are going for polyenes. They are so from C4H6 to something like C60, H60, and here we are looking at a wave function. A single determinant, we are increasing the system size, so the number of parameters increases, and we can compute the energy and the derivative and also the Hamiltonian acting a derivative with roughly a proportional cost to the cost of computing the energy alone. Okay? So the ratio is about 3. On this side, I'm showing what's happening for geometry optimization, so you're computing forces. And on the x-axis, we are having the number of determinants, so we are using larger and larger Jastrow-Slater wave function, and we are increasing the system again from butadiene to something like C60. We are not using linearity of the molecule. And what we are having is that the cost of computing energy plus forces divided by the energy alone is again proportional to about, so within a factor of 3. Okay? So if you're willing to compute the energy, you can get out derivatives and not so much more cost. In addition, there is a toolbox of optimization tools. Giuseppe mentioned the stochastic configuration, but also gradient-based method and other approaches. And we are therefore in a situation to actually treat quantum Monte Carlo as internally consistent. So obtaining geometry and variational parameter in a consistent manner. So now you still need to choose your many-body wave function, and here we focus on Jastrow-Slater wave function. You already mentioned you have a Jastrow factor, correlation factor, and a sum of the terms. Another question is whether we really need a multi-determinant expansion in quantum Monte Carlo. I mean, often if you look in the literature, people use a single determinant. Now, if you go multi-determinant, how do you choose the expansion? And then if you work very hard in variational Monte Carlo, you optimize everything. The question is, do you even need diffusion Monte Carlo to actually on top of your VNC? So now for many years, what we have been doing, we have been using a type of determinantal expansion, which is often used in quantum chemistry, which is called the so-called complete active space. Okay, so the idea is you're having a molecule, so it's a small cyanide dye, you're saying I'm starting a pi to pi star excitation, and you decide over which set of orbitals you want to have, let's say, a full CAS, meaning a full CI, of which you then maybe optimize the orbitals. So here you can say is a pi to pi star excitation. I build, you have two W occupied pi and unoccupied, which you can build out of 2p. And therefore you will have, 4 electrons in 3 orbitals, in a total of 3 determinants. But then as your system increases and you're going from 3 heavy atoms to 11, you will have more electrons and also more orbitals, and your number of determinants will grow. And so you will be actually correlating a lot of determinants which you might not need, but moreover also you're only correlating a subset of electrons. For instance, you're having a pi to pi star excitation, and the so-called sigma electron might actually relax, and you're not including them in terms of static correlation. Okay, for a long time, actually, I thought that doing a DMC on it would have cured the problem, but we will see in a moment that this is not the case. Now, in the last few years, we have actually been also exploring a different way to build the determinant expansion using so-called selected configuration interaction approaches as a way to look in a deterministic manner, but automatic manner, a way to generate a many-body, a multi-determinant wave function. And the idea is you start from some set of determinants, and then you explore space, and the way you actually decide whether a determinant is good or not is based on their second-order energy, perturbation energy correction. Okay? And what, again, people in this field would do, then they would compute, the variational energy, the CI energy, and do the extrapolate with respect to the total PT2 correction, which is becoming, smaller and smaller as the expansion becomes larger. Okay? And the question is, if I'm choosing these in an automatic manner, will this be better than what I was trying to do before, and will this give me something which is more common? So now here I'm gonna show you the result, so the impact on variational Monte Carlo and diffusion Monte Carlo, excited state. What is the impact of choosing different wave function? I'm looking at this cyanide dye, relatively small, vertical excitation energy, And here on the x-axis, we are having different wave function. Okay, so you can say in the same way that for the ground state people use a single determinant, I can use a homolumo, for instance, you know, two determinants for the excited state, and I'm up here at the variational level. So the whole scale is 0.5 eV. Okay, so I'm up here at VNC, I do a diffusion Monte Carlo, it helps me a lot, but it doesn't bring me down to what are reasonable, believed, you know, well, accurate, relatively accurate estimation for this system. Okay, then I can say, oops, sorry, I can say I do a CI single, I add a single, my variation Monte Carlo worsens, diffusion Monte Carlo perhaps somewhat better, and then I can go to these complete Tati spaces. So they're full CI in a small set of objects. Okay, I can include the pi, I can include more pi, I start to include the sigma, I truncate. I have 73,000 determinants. The VNC is slowly but surely, but slowly going down. Diffusion Monte Carlo helps, but I'm still far away. Okay, and here what I'm showing is the result of actually doing a SIPSI expansion. Okay? I have 1,000 up to 18,000 determinants. We're optimizing all parameters, ground and excited states. And what we're having, we're finally, let's say, within the bracket of, you know, within chemical accuracy of the reference result. Okay? And what also we observe that when we are good, diffusion Monte Carlo is practically on top of variation Monte Carlo. So the message is we do have a strong dependence on the wave function, but let's say a relatively compact wave function can recover what we want within VNC and VNC. So now here what I'm showing is two different other small systems. They are challenging for different reasons. And again, you know, we will forget about the choosing some set of orbital based on our chemical intuition, and we are just going to use this selected CI, so automatic manner, and we are going to, I'm listing the total number of determinants for both states, and what you're having is the VNC and DNC are very close to each other. Here we are going down to a scale of 0.06 eV, so it's very small, and you are within, you know, chemical accuracy of the best result. Okay, and again, for us, you know, a few thousand determinants is a handful of determinants, and as I said, the diffusion Monte Carlo is no longer needed. So how do you do this? So there are few ingredients, well, two ingredients. First of all, we are dealing with multiple states, so we are doing expansion, ensuring that they are balanced. Okay, they might have actually different number of determinants if they have different symmetry, or the same number of determinants, but we might actually adjust the selection criteria to so that, you know, the expansion at the CI level either have the same variance or the same total PT2 energy, which we how can I say, we can view it as the error with respect to the full CI limit, and therefore you are actually requiring that the two expansions have kind of the same error. Okay? In addition to this, we fully optimize the wave function, and we can get chemically accurate excitation with few determinants, few being a few thousand. And as I said, no need to do DNC, and actually often what we use as a validation criteria is how close the VNC and the DNC excitations actually are. So having this protocol, we can actually start to also relax the geometry in excited state. We can excite our molecule, and often, you know, you be out of your equilibrium, and the molecule will do something. Okay, so this requires to generate a lot of wave function for ground and excited stage, and evolve them along, you know, as the geometry relaxes in the excited stage. So here what I'm showing is three small molecules. So in one case, you're having buckling. Here is just an elongation of the bond, and again, some sort of buckling also for thiophene. I'm showing the maximum absolute deviation, 0.01 angstrom. I consider it good. We are comparing to some available reference, reasonably good reference. I'm showing CC2 and CC3 in green. So these are two couple cluster approaches. This is a different quantum chemical approach sometimes appearing in the literature for geometry optimization in the excited states and also for dynamics in the excited stage. And red is variation Monte Carlo. So we are within 0.01 angstrom, so I would say, you know, rather accurate. So of course, so far I only showed you quite small system, and the question is, can I go to larger system, and how is the size of the wave functions, this latest wave function actually worsening? Here what we are doing, again, the same type of system I showed before. This is a cyanide dye. We are going from something like 3 heavy atom to 19. Okay, and finally we are actually pushing this simulation in a region where we don't have couple cluster result. Okay, so they are too heavy for memory, at least for our machines, to actually do it. And so the 0 here is diffusion Monte Carlo. Variational Monte Carlo is the green. You can see the scale is very small, so that's chemically accurate. And here is full extrapolated full CI for the smaller sizes where is available. And in terms of wave function, what we found is that actually we need fewer determinants to extrapolate the excitation energy. It doesn't mean that we need fewer determinants to actually get the individual states, but for the excitations, we found that actually the small system is more difficult than the large system. We go from 10,000 to 5,000. And as I said, we are actually finally getting into some region where, let's say, CC3 start to become costly and for many people prohibitive. Okay. Now, so far, I have shown you how to what kind of wave function we have been using, how we've been trying to actually improve our accuracy. But maybe I will spend a few words to actually say how we optimize the wave function in the excited stage. Now, our method of choice is energy minimization, and of course, if there are different symmetry, that's easy. But if they had the same symmetry, you can either use a state average approach where you're having an expansion. You can decide that the state share the same Jastrow and the same orbital, and they have different CI coefficient, and you can optimize in a state average fashion. So you find a balance for a state as regards Jastrow and orbitals, but you have different coefficients. Or you can use state specific with some orthogonality constraint. And this was used in various contexts, for instance, Fusi QNC, it's in Giuseppe, this is Carleo, and recently Wagner within the variation of Monte Carlo. Now, another approach which was very much pushed forward in recent years, and it would be indeed very convenient, is to go back to do variance minimization, okay, like we are doing in the early day of quantum Monte Carlo, because that has the convenience that you can just treat one stage at a time. So, for instance, you can use such a function, using omega as your target energy, which you modify following the average energy during optimization. Okay, you can also use different functions, which we tried, but the results I show are pretty much the same. Okay, so we can start again from our cyanide dye. Here we're optimizing the ground and the excited state. The variance goes down. You say, fine, I'm happy, I'm converged. And now I'm looking at the energy, and the energy, of course, is not the minimal energy. And it nicely converges to a value, and we find the energy and variance at the level of VNC are rather equivalent, okay, which is good. But then we try to actually say, okay, fine, great. Now we go to bigger wave function, and what we saw that for the same system, if I go from 50 to 7,000 determinants in a wave function which is clearly better, I'm not showing the variance will converge for both, but while the ground state appears, the energy appears to actually converge, the energy of the excited state will start to ramp up, okay, grow and grow. And this is independent of the choice of optimizer or the choice of functional to obtain the minimization of the variance, and therefore, let's say it is impossible to compute an excitation energy. You can get whatever you want, depending on where you stop along this law. So what we found, somewhat surprising, that the variance minimization can be problematic. Of course, we know that in the limit of exact wave function, as the wave function becomes larger and larger, the variance must have minima. Okay, but these are a reasonable wave function. I'm talking about 7,000 determinants. And this growth is often observed for different systems and different wave function. So now if you go back to the situation where we are seeing the energy ramping up, you can actually see that it's kind of converging to a higher excited state. So it was saying that, for a proximal wave function, where you're still far away from your target, the optimization might escape the target state or finding practically no barriers. Now to analyze this better, we look at a small expansion over 13 determinants, and you can generate 13 eigenstates. They all will have different variance. You optimize the variance, and we'll all go to the same minimum, which is very good. The problem is, if you're looking at the energy, that they will all go to the second stage, to the excited state, not to the ground stage of that symmetry, okay? And because this state has a lower variance than the other. So the problem is that the state with the lower variance may not be the one you desire. And because of the lack of barriers or near lack of variance or barriers, you might actually lose the state you care. And therefore, generally speaking, we don't do variance minimization, but we are going to use energy minimization because it's safer and more fast. Now, for energy minimization, of course, we used in the past a lot of state average optimization. Nowadays, we use state specific. We are using this penalty function. So you're having the energy of your state plus you're essentially having a cost for to ensure orthogonality. Okay, so and we are doing it on all states different the states of consideration, because even if you're doing the ground state and you're moving your geometry, state might cross. Okay, so we are treating all states on the same footing. And we are optimizing all wave function in a single run using correlated optimization and a guiding wave function in such a way also to get a more balanced description, optimization of the state of interest. And so far we have been applying these to double excitations. So in the previous examples, we have been mostly looking at excitation which are of single character. And now we move to double. I mean, we would like to show that we can do a single, double excitation, so different type, a larger system, small system, to give a feeling that, okay, QNC is indeed robust. So why doing double excitation? These are very problematic for high-level coupled cluster, okay? So CC3, CCSDT wouldn't get them. You would need to go to quadruple to actually get them. So I'm showing tetrazine. Here are excitation energy, again, a scale of 1 eV, couple cluster is up here. This is CC3 and CCSDT, multi-reference PT2, and these are different QNC with this selected CI wave function with between 400 determinant and 10,000 determinant. So a problem we had in also doing this double excitation is that the reference, you know very well often what to take as a reference. Okay, so we doubt ourselves for some time, we're having now, as I'm going to show, enough confidence to say that we are doing okay. So here I'm showing a very small system, and what I'm showing is different wave function type, but again, the complete active space type in state average, you can do state average, state specific, and the performance is rather equivalent for this system. And now if I do SIPSI, also for this system, everything is okay, variational Monte Carlo, and diffusion Monte Carlo. You can see the CC3 is higher by 1 eV, and we are perfectly compatible with extrapolated for CI. There's another one, Glyoxal. Glyoxal, again, I'm looking at different type of wave function. The performance in this case of a relatively small CIPSI is in state specific is quite satisfying. Again, CC3 very high. And we are, okay, so here we start to have trouble with extrapolated CI to actually get a reference. And as far as we can see, we are in agreement, and okay, we can take the QNC as the current reference. And now here what I'm showing is another one where this is larger, and there are two states which are considered, one is considered difficult and the other one easy for some reason. And we're getting, if you're doing CC3, we are getting essentially that we are off for each state by 1 eV, and the relative order is actually swapped. And again, here is very difficult to do extrapolated full CI but you can get an extrapolation of the difference, which is in very good agreement with one. And finally, his work is finally almost out because despite the lack of references, we think that's pretty much among the best calculation on this type of excitations and systems. So now I will conclude. So what we've been really searching was a protocol for modeling photo excitation. So to generate wave functions which are compact being 2,000 determinants, balanced among the states. We want to get not only excitation, but also geometry. And of course, the big question is, how do we move to larger systems? We show for the cyanines that selected CI is working well, but it's still exponential. And so eventually, the number of determinants will be smaller and smaller, and we'll encounter problems. And indeed, thinking about different type of wave function is very important. If we could have some physical insight also from this multi-determinant neural network, it would be very useful. As I also showed, that use energy minimization, various minimization can have trouble. We compare state specific and state average. For the system we look, there is not much difference, but state specific is more appropriate and is surely very effective for double excitation. And we are currently exploring the use of forces in the excited stage for ND simulation, but that's very much in progress. And also looking at excited stage, relaxation has the advantage that for not always, but sometimes, the time scale are significantly smaller. So we have a hope to actually do some ND there. Okay? And I conclude with the collaborators. So the Monica Dash and Alice Puzzo-Crea, she was a PhD student with me, now she's about to finish, and they are the ones who have been doing most of the work. Ravindra and Shinden Stuart Shepard are postdoc, working on the code and on double excitation. And then, my senior colleagues, Saverio Moroni, a dear collaborator, Anthony Semama is our expert on selected CI, and then a local colleague with whom we talk a lot, Wim Brielsen in Twente. And thank you for your attention.